Okay, here's what we're going to do for today. I want to go through one quick thing, and then I'm going to let you get back to work. So I want to go through, we're going to talk about solving multi-step equations. So these papers, here's kind of the way I've decided we're going to do this. So the white ones are notes. Those will just go in your notebook. You can write stuff, like stuff we're doing in class today. If you need to write something down, just put it on there, like on the sides and the margins or something. It won't be that much to write. The orange ones are going to be homework, but on the paper homeworks, I'm going to go ahead and just post the solutions online today. And then from now on, when we do that, I'll just post solutions to those, so you can check your work, redo them if you need to, if you miss any of them. There will be a Moodle assignment that goes with this that I'll put up probably today-ish. It'll be either at lunch today or might be after school, but it'll go with this. Okay, questions? All right, so let's talk about this. Let's talk about solving equations. And the point I want to make here, and this is the big one, this is really important, is how do we use the order of operations tree when we solve multi-step equations? Now we're going to start easy. We're going to start with linear stuff. So these will be extremely simple to you. They won't be a big deal. But I just want you to see them in the context of how we're going to continue to do this throughout the year. So here's how this works. We've got our PEMDAS tree, or GEMDAS, whatever you want to call it. So we talked about simplifying. The simplifying direction is top to bottom. What do we do when we're solving? Bottom to top. So we reverse the order of operations direction. And when we solve, which is the same thing as isolating a variable, we go bottom to top. Okay? Now there are going to be some instances in algebra that we'll run into throughout the year where we have to do something different. Right? There's some other strategies we have to use where we can't simply just isolate a variable. It means we're going to get multiple solutions and it breaks down. But to some degree, this is always going to be useful. And in many cases, this is all we need to do. Okay? So when we're given an equation like this one, for example, solve the equation. For a second, let's just talk about what it means to solve. And we'll continue this discussion. We're going to do a quick review of graphing linear equations. And we'll come back and ask the question, okay, what do the solutions mean in terms of the graph later? But for now, let's just think of this in terms of algebra, no graphs. If we're asked to solve an equation, what does the solution look like? And let me see a hand, somebody wants to be brave here. What's the solution of this equation going to look like?
X.
Yes, sir.
X equals the answer.
X equals a number. Okay, good. What's important about that number? And we'll get the number in a second. What does that do that makes it a solution? Yes, sir.
Makes both sides equal.
Okay, so it makes both sides equal. In other words, it makes this equation work, right? In other words. So a solution satisfies an equation, or it could be an inequality. We'll talk about inequalities soon too. And we'll get to those later. But in math, we say if it satisfies an equation, it makes it true, it makes it work. Okay, so solutions can be a single thing, or they can be a solution set. We could have more than one value that works also, right? For linear equations, we're only going to get one. But later on, when we talk about quadratic equations, we're sometimes going to get two. We talk about polynomial equations, we might get multiple. When we talk about inequalities, we're going to get a set of an infinite number of values of x. And we can express the answer with inequality notation, and we'll get to that soon. But remember that when we talk about a solution, we're talking about the value or values of the variables that satisfy the original equation. Okay? So now let's talk about how we get there. Well, you already know the steps. What's the first thing we're going to do with this equation? If you were going to sit down and do this, I guarantee you just reflexively know what steps to take. Somebody be brave here. What's the first thing you do? Yes, sir?
Distribute.
Okay, we distribute. Okay, we would distribute the 7, right? So we'd end up with, if we distribute the 7, we get 7x minus, 42 equals 10x minus 78. Good. Okay, what else?
Minus 7x.
Okay, we'd subtract 7x, very good. So why are we subtracting 7x? Good, because we want to always push the variables, and I'm going to talk about this kind of visually up here. This is how I'd like you to kind of start to think about this. It's just better. We want to push the variables to the side of the equation where you have a positive number of them, because it's easier to isolate them that way, right? So we're going to push the 7x to the right, and we do that by subtracting, right? So we get minus 7x. That's good. That's going to get rid of the x's from this side, and we're going to get a 3x on this side. Now, while we're at it, you guys are a more advanced class. We want to combine steps when it makes sense to do so. What's the other thing we're going to want to do here? Okay, we're going to add 78. Now, we don't want to add 42. Why are we adding 78? It's not so we can get a positive number. There's a different, better answer here. Good, because our goal is going to be to isolate the variable, and so we want to start pushing the constants away from the variables, right, to get the variable by itself. Solving and isolating are identical. Isolating a variable means we're solving for it, okay? So we're going to add 78 to both sides, and it's just a coincidence in this case that we happen to get a positive answer. It wouldn't have to be. So the constants go away from this side, and what do we get here? 36?
Yeah.
Okay? All right, so now we've got a single instance of the variable. So what have we done here? In essence, what we've done is we've been working down the blue side of this equation, right? We've been trying to simplify this equation by, we multiplied, there were no parentheses to deal with. Well, actually there was. There was a set of parentheses, but there's nothing we were able to do inside, right? The x and the 6 were not like terms, so we couldn't combine them. And so we worked our way down. And so we found that we didn't have to deal with that. There were no exponents, but there was an instance of multiplication, right? We had to distribute the 7. So we're just simplifying the expression. We haven't even really started to solve it yet, right? And then we got down to addition, subtraction. Well, we combined like terms, really is all we did, right? When we pushed the x's all to one side, we were just combining the x terms on one side of the equation, weren't we, right? Okay, so we got down to the add, subtract, and now we're going to isolate the variable. Okay, so how do we isolate the variable? Notice that we get to a point here where there is a single instance of the variable. And I'm going to say this about 1 billion times this year. If you can point to a single variable, then you can isolate it, right? So we got a single x up there. All we have to do now is start working our way backwards through the order of operations, and we can isolate the x, right? There's only one thing to do here. What is it? Divide by 3, right? But now we're working up the solve direction, so we'll reverse the order of operations. We're going to work our way down to simplify things to get a single variable. Once we get a single variable, we'll reverse it and work up the other way, okay? So if we divide by 3, we get what? X equals 12, okay? When you're solving equations, now, I get that if, when you're doing homework, you probably just check the answer, but on a test, what should you do every single time on every test you take for the rest of your life if you're solving a math equation? Before you submit it, for example. What do? Well, check it. Well, it's very easy to plug it in because we just have to see if it does satisfy the original equation. Plug it in and see. If I plug in a 12, I'm going to get 7 times 6 is 42 equals 60. Hang on a second, did I do that right? Oh, 120 minus 78, yeah, it would work. Right, we'd get 42 on both sides. So bingo, okay? All right, how about another one? How about one like that? Okay, what looks ugly about this one? Fractions, right? Fractions. Fractions are just hard to work with. Doing arithmetic with fractions is more difficult. You're more likely to make mistakes. Adding and subtracting fractions is harder than multiplying or dividing fractions, right? Because you have to get common denominators and all that stuff. So what do you recommend here? I mean, we could go through the same steps we did before, where we could just push the x's to one side and the numbers to the other side. Better idea. Yes, sir?
Multiply the entire equation by 6.
Yeah. Okay, so this is the trick, right? We call this clearing the fractions. So before we do anything, If you have a situation like this where you have a bunch of terms, nothing's being multiplied here, right? Especially in this case, if nothing's being multiplied, you want to go ahead and just, I've got 4 separate terms, I've got some fractions in there. Immediately, the first step is always clear the fractions. And what's the recipe for clearing the fractions? What do I multiply by? How do I know to multiply by 6? Yes, sir.
Multiply by the largest denominator as long as it's a common factor of the other denominator.
Okay, so it may not actually be one of the denominators, but we want to multiply by the least common multiple of all the denominators. In other words, what would the least common denominator be, right? If we were going to write a least common denominator, what would that have to be? And that number is what we're going to multiply both sides by. So we'll multiply both sides by 6. Okay, so if I distribute the 6, and now what do I get if I distribute that 6? Okay. And from there, it's a piece of cake. Combine, we push the x's to the right, push the numbers to the left, and then we won't even have to divide that. Actually, yeah, no, we won't. We'll be done, right? We'll have an x. Okay, let me make up a little harder one. How about this? What if we've got something like, about that one? Ugly, lots of nasty fractions. Right, would everybody agree that would be a really inconvenient problem to try to deal with if we didn't clear the fractions, right? Okay, so we definitely want to clear the fractions. I've got 4 separate terms, fractions in all of them. What's going to be the number by which I'm going to multiply both sides? 40. So the least common multiple of 8, 5, 4, and 20 would be 40, because we can all identify it, right? Okay, I want to show you one other little trick here. That's an important one. Okay, any suggestions how I want to go about distributing here? So when I, for example, when I make the distribution to this first term, when we multiply fractions, we multiply straight across, right? So technically I would have, well, hang on a second. Oops.
Okay, I was already counting.
All right, so I by the rules of algebra, the normal rules, I'd want to multiply straight across, right? So I'm going to get 200 over 8 times x. That's a pretty big ugly fraction though, right? Sort of hard to reduce that. And you could do it, but you have to think about it a little bit, right? Is there a better plan? Is there a better plan? Should I multiply across and then reduce the fraction? Why don't I cancel? Right now, think about this process. When we're clearing fractions, that number 40 has been handpicked because it is the most convenient number. It's the smallest number that all of these denominators are guaranteed to divide into evenly, right? So doesn't it make more sense instead to reduce first and then multiply so you're dealing with smaller numbers? Right? It makes it a lot easier. And it's, you know, it may not seem like that big a deal when you're working with kind of these introductory problems now at the start of the year, but later on, when the problems get harder, it could make a very big difference, right? So let's do that. When we when we multiply here, we get 40 over 8. Well, 40 over 8 reduces to what? 5. Okay, so we can cancel the 8. And we know that when we reduce, we're going to get a 5, which we're going to multiply by the denominator. And what do we get? 25. Much easier. That's a lot easier than reducing 200 divided by 8, isn't it? Right? So the first term we get is 25x. What about the next one then? 40 over 5 is what? 8 times 3 is, well, way easier, right? How about over here? 40 over 4 is times 3. 40 over 20 times 17. That's easy, right? Now it's a piece of cake. From there, I don't think we have to even go through it. We just push the x's to the right, push the numbers to the left, and divide, right? Oh, actually, let's do that. I want to make one point here, though. One last point on this one. So if we do the math, x's go right. So how many x's are we going to end up with? 5x on the right, good. Numbers go left, so what do we end up with? Okay, and then I divide by 5, right? So I end up with x equals negative 58 fifths. Okay, I get a fraction in my answer, but so what? I didn't have to ever deal with the fractions. The only time I had to actually work with the fractions is when I wrote it down at the end. Right? Right. Okay. You know what occurs to me? Maybe I ought to do one more quick example with this. How about... Okay, what about this one? Do you see this is a little different? A little different, right? So what am I going to do this time now? I've got this 1/2 out in front. I've got a couple options with this. Clearing the fractions, I got to be a little careful. If I try to clear the fractions now, the mistake people often make is they double multiply, right? So what would the least common denominator be here? 40 again, it looks like probably. 40. So if I were to multiply both sides by 40, how am I going to do that? When I distribute the 40, would I have to multiply the 40 times this and this and this? That'd be double multiplying, right? I'd multiply the 40 times the 1/2 and then distribute that. Okay, does that make sense? So you run the risk of making a mistake here. This is different than the previous example because we didn't just have a bunch of terms. So we want to get to the place where we have just a bunch of terms and nothing being multiplied. So how could we get rid of, this is the culprit, isn't it? We've got this 1/2 out front that's kind of muddying up the waters here. We'd like to get rid of that. What are some ways to get rid of that? We could distribute it, right? But distributing it means I'm going to get big fractions in there. What's one thing I could do instead? Oh, okay, I could clear the 1/2 by multiplying both sides by 2, right? So step number 1 might be, let's multiply each side by 2. So on this side, I am multiplying by 2 over 1, okay? Now, there's no guarantee this time that I'm going to get things that reduce. Okay, so this time I actually do have to just distribute the 2. I may be able to simplify by reducing, but there's no guarantee, right? Because I haven't picked a common denominator. I'm just getting rid of the 1/2. So when I multiply that through, the 2 times the 1/2 cancels. So on the left side now, I get something better. I just get 7/8 x minus 3/4 x, nothing being multiplied. On the right side, what am I gonna get? If I distribute this 2, what's gonna happen? Okay, 26 over 10. I could do the 2 over the 10 does reduce to 1 over 5 in that case, doesn't it? Right, so I could write this just as 13/5 x, and then 2 over 1 times 1/2 just becomes a 1. Okay, now this looks like the first example, doesn't it? Right, so now I could clear the fractions. And what would be my, I guess it'd be 40 again, wouldn't it? Right, distribute a 40 all the way through, and this time that is the hand-picked number. It's the least common denominator of all the fractions, so I could do the same way I did last time. I could just simplify first, and I could reduce and then multiply by the numerator. Okay, see the point? Okay. All right, what are we out here in 2 minutes? Is that right?
Yeah.
Okay.
Yes.
All right, that's probably good for today. So work on the orange stuff. You got the stuff on Moodle tomorrow, extra. Okay. So tomorrow I might spend 5 minutes, but I got something kind of different for you on the Friday going around. We'll do something other than just play down.
Do you talk about physics?
Oh, we'll talk about a little physics maybe, yeah? I want that turned in after roundup, how about? Okay, sound good? The yellow one I want tomorrow.
Okay.
Yellow one tomorrow, orange one you can have
And
for
when
roundup.
you want to do the computer stuff then?
Oh. Yes. Is this stuff on Say it again. Is this stuff on this stuff we just talked about?
No, the computer assignment.
Is it, oh, I mean, honestly, I wouldn't care if you guys just worked on, if you want to work on overround, it's no big deal. I mean, it's, why not, get all that time off. I won't put anything in the book until after. But see if we get the paper ones and just get it out of the way. Except the orange one. Orange one you keep. That's over roundup. Like my tea count?
That almost caught me. That almost made my paper.